Walk into any comic shop, and you'll hear arguments over who possesses the strongest punch. Fans use conflicting lore to decide who hits the hardest. We are stripping away the fan bias, the magic, and the plot armor. Today, we are evaluating these impacts using the strict, objective rules of physics. To measure raw striking power, we use two metrics. First is linear momentum, mass multiplied by velocity, calculating the physical transfer of motion into a target. Second is kinetic energy, measuring the absolute capacity for destruction. Crucially, in this equation, velocity is squared. Human intuition tells us that a massive, heavy brawler is going to deal the most damage. But because velocity is squared in the math, we have to ask if speed is the actual secret to generating ultimate power. To test this, we are putting 4 specific subjects through the math. We will scale up from sheer brute strength to light speed movement, analyzing the Hulk, the mighty Thor, the alien Superman, and the Flash. This comparison matrix tracks our evaluation. We will log each hero's specific mass, their maximum striking speed, the physics paradigm they operate under, and their final energy output. To find the definitive truth, we have to abandon what looks cool on a page and let the equations dictate reality. We start with the Hulk. He serves as our baseline for classical brute force, relying entirely on the physical weight behind his fist. For our input metrics, we assign a standard Savage Hulk an estimated mass of 600 kilograms. He moves surprisingly fast for his size, so we'll set his striking speed at Mach 2, roughly 680 meters per second. When we run those numbers through the kinetic energy equation, the mathematical outcome is 138.7 megajoules of energy. To put 138.7 megajoules into perspective, it is the exact physical equivalent of being hit by a 20-ton commercial truck traveling at highway speeds, with all of that force concentrated entirely into the surfaced area of a human fist. This chart maps speed on the bottom axis against energy output on the vertical axis. The Hulk's punch lands relatively low on the curve. Now we shift to Thor. This represents a massive drop in physical mass, but a massive increase in localized velocity. Thor's hammer, Mjolnir, weighs just 20 kilograms, but he swings it at Earth's escape velocity, which is 11,200 meters per second. Escape velocity is the minimum speed an object needs to travel to break free from a planet's gravitational pull. The math puts Thor's kinetic energy at 1.25 gigajoules, matching the detonation of a small tactical nuclear warhead. On our chart, the difference is clear. Despite swinging a weapon weighing 580 kilograms less than the Hulk, Thor generates nearly 10 times the energy. Within the strict confines of classical mechanics, sheer bulk loses out. Because velocity is squared, it acts as the dominant force multiplier in the equation. The math escalates dramatically when we introduce Superman and evaluate what happens when an object approaches the speed of light. Superman's input metrics are a 100-kilogram body mass moving at 99% the speed of light. At this exact threshold, classical physics fails completely. We have to switch to special relativity, the branch of physics governing objects moving near light speed. To calculate power here, we need the Lorentz factor. This is a mathematical multiplier that calculates how mass, time, and space warp at relativistic speeds. Applying the Lorentz factor to a 100-kilogram fist yields a relativistic energy output of 5.48 times 10 to the 19th joules. That number represents a planetary extinction event. It is roughly equal to the detonation of the Tsar Bomba, the largest nuclear weapon ever built. A physical strike carrying that much energy would shift Earth's orbit. When we update our master chart, the vertical scale has to compress tightly just to fit Superman onto the graph, resulting in a sudden, violent spike in the curve. Which brings us to our final subject. The Flash generates force by pushing the absolute mathematical limit of the physical universe. For his input metrics, we place his 75-kilogram mass at a velocity of 0.99999999999 c, just a fraction of a single meter per second below the speed of light. At this precise velocity, the Lorentz factor scales toward infinity, the entire equation breaks down, and the line on our chart goes completely vertical. The theoretical impact of this specific speed generates infinite kinetic energy. His mass would become so dense it would collapse into a local black hole. Crossing the light barrier completely changes the nature of a punch. It stops being a localized physical attack and becomes a reality-collapsing event. We have calculated the power, but we have to address the hidden cost of the Flash's infinite mass punch. Unleashing infinite kinetic energy has severe consequences for the environment. In the real world, the friction of moving that fast through the atmosphere forces oxygen atoms in the air to undergo instantaneous nuclear fusion, turning the surrounding environment into a stellar ignition point. This introduces a central trade-off for sci-fi writers and world builders, the reality barrier. This quadrant chart maps the environmental collateral damage on the bottom axis against the impact force on the vertical axis. The Hulk and Thor occupy the moderate zones. Superman and the Flash cluster at the absolute mathematical maximum for both. You cannot grant a character relativistic speed without completely sacrificing the physical environment they exist in. To make these stories work, creators have to invent magical workarounds, like the Speed Force, to ignore friction entirely. Without those workarounds, writers have to stick to classical mechanics to keep their fictional cities standing. But if we are answering the debate definitively with raw mathematics, the Flash possesses the strongest punch. Physics proves that velocity is the ultimate weapon, but the math also reveals a terrifying reality. To hit an enemy with infinite power is to definitively destroy the world you are trying to save.